It's my pleasure to welcome Pablo Soberón of Northeastern University, who will speak to us today about Tverberg-type results, weak epsilon-nets, and the probabilistic method.
Okay, well, thank you. So what I want to talk about is a family of results about points in real spaces. And what I care about is the combinatorics of finite families of points. Okay, so I give you a family of a family of points in order. I look at the convex hull of the subsets, and I want to understand how they intersect and which properties they have. Okay, so as a first example, if you look at what happens in OR2 and say 4 points, there's basically two ways they can look. 4 points in which no three of them are in a single line, right? It's either a triangle is the convex hull, or they make a convex quadrilateral. And in this case, I can, well, it's basically a triangle containing the other point. Or here, if I take the diagonals, it's two segments which intersect. Okay? So there's an old result by Braddon from 1921, I think, which says that this happens in high dimension. So if I give you d plus 2 points in order, then you can always do something like this. Split them into two sets so that the convex hulls intersect. So there is a partition AB such that the convex hull of A and the convex hull of B is not empty. So this is the sort of things I want to understand. Okay, and even back in the 1920s, Braddon thought that this was completely trivial. This was just a lemma, and well, he was trying to prove Helley's theorem. And the interesting question becomes, well, what happens if instead of splitting things into two pieces, I want to split them into more pieces, right? So I want a partition into 3 sets or 4 sets or so on, and I want to know how many points I need to get some mechanics. Here, d plus 2 is optimal. If I take d plus 1, you can just take the vertices of a simplex, and then no partition satisfies this. Okay. So in the plane, for example, if I give you 7 points, hopefully I can do this right. You can always find a partition into 3 pieces so that the convex hulls intersect.
So the points will be somehow in joint position?
Yeah, I mean, they don't have to, but...
So what if they're all on the same line, right?
Well, if they're on the same line, then you have a lower dimensional problem, and you need less points. So if you have linear dependencies, which you shouldn't have by general position, it usually means that you have more partitions of this type. Okay, and any configuration of points which has collinearities, you can approximate it by configurations of points in general position. So if you solve the problem in general position, you get all the results. You can get results. Right. So this took a bit longer, but roughly 45 years later, Tverberg proved that you can always get partition. He gave the number of points you need to do things like this. Okay, so now it's the number of points you have is or minus 1 times d plus 1 points in or d. And or is going to be the number of pieces I want in my partition. Okay, so there is a partition of them into or sets A1 up to A or, such that the intersection of the convex hulls of the AJs is not empty. Okay, and the number of points is optimal, and again, this is a nice result in combinatorial geometry. It has nice consequences in the field in computational geometry. If you like combinatorics, this is usually combinatorial enough to make you happy, and it also has some very nice versions, which are often called the topological versions of Tverberg's theorem, which have been a driving problem in topological combinatorics. I may get to some of those things by the end of the talk. But if you like combinatorial geometry, one of the nice... So I want to talk about a generalization of, or an extension of this theorem. And I have two motivations. So the first one is an application of Tverberg's theorem, and this is what we call the existence of weak epsilon-nets for convex sets. So this is a theorem by Alon, Baraň, Furedi, and Clayton from 1992. And it says the following. What I want to do now is I'll give you a very large family of points in order. You can think of this having 10 million points. And what I want to do is to approximate this family with a small family, right? So I only allow you to use, say, 100 breadpoints, and I want a set of 100 points that approximates this big set in a very nice way. Okay, so the question is, how do I find a set of 100 points which, combinatorially speaking, does look a bit like this one? Okay, so one thing I could do is maybe whenever I take 10% of the white points and I look at their convex hull, I would want a red point inside, right? Anytime I look at a local small subset of white points, I should get a red point inside. And what they prove is that if I give you the fraction of the fraction of the size of the subsets that I want to be checking, how many points do you actually need for something like this? So what they proved is that given the fraction epsilon bigger than 0, and the dimension of the space I'm living in, there's an integer n, which depends only on these two numbers, such that for any x in OR there is a set C with size bounded by this n, so that the following happens. Such that for all subsets y of x, which are large enough, so they have at least an epsilon fraction of x, the convex hull of y contains a point of the set. Okay, so these are my red points, and this is just telling you that whenever you look at a small subset of x, you always find this. The cool thing about this one is that this number doesn't depend on the size of x, okay? Which is a bit surprising. If you take, for example, a random sample of x and you want to see if it works, you get something which depends. So the number of points you might need here is logarithmic in this one, but it still grows to infinity as the size of x goes to infinity. Okay, so this is a bit surprising that you just need a fixed number. And it's just, they get this by using Tverberg's theorem in sort of a very greedy way. They try to make this red set 1 by 1 point and using Tverberg's theorem over and over again to get this. Okay? So one of the things I want is to get a Tverberg theorem that basically has this flavor, that whenever I give you a big set and whenever you look at small subsets, you see Tverberg partitions in them. Okay? Right, so one question is a Tverberg theorem with a similar flavor. Okay, so I'll be very vague about what I mean by this.
Is it constructive at all? Can you program a computer to find the set?
So if you have an oracle that, given a set, gives you a Tverberg partition, you can do it. Okay. The problem is that the algorithms to find Tverberg partitions are actually far away from the optimal case.
I was just thinking this is the backwards problem from like what Paul Hand is talking about. You want to be given the small number of points and produce the 10 million instead of having the 10 million and producing the small number.
So, right. So for the algorithms that give you Tverberg partitions, They don't work as optimally as this. But so if I give you n points, Tverberg's theorem tells you that you can split them into n over d plus 1 pieces. The efficient algorithms, I think with n over d cubed pieces, you can get stuff like this. And I think even this version is strong enough to prove something like this, maybe with a very bad n here. Okay, so you could use those iteratively to construct this. The size of n in terms of epsilon and d, that's sort of a big open problem. And there are bounds which are between slightly superlinear to exponentially in 1 over epsilon, I think. I would have to check that. But yeah, the bounds are very far away, the ones we have. Okay? Great. Good. So let me give you another motivation of why I might want something like this. And this is related to an extension of this result here by David Lorman. So what he wanted is, okay, if I give you 4 points in the plane, you can get a random partition like this one or this one. But if I erase any of the points, it sort of breaks things down, right? You have a segment and a point, or maybe a triangle by itself, or a segment and a point. Things stop working. So what he proved is the following in the 70s, that now instead of giving you d plus 2 points, now I'll give you 2d plus 3 points in OR-D. Okay? So what you get is that if I give you this many points, there is a partition into 2 sets, A and B, such that for any x in the set, or even in OR-D, it doesn't really change anything, the convex hull of A minus x and the convex hull of B minus x still intersect. The points of intersection may change as you change your x here, but they always have at least one point of intersection, right? If I give you 6 points in the plane in convex position, you might try to do something like this. So any point I remove, it's a segment and a triangle that still intersect. But this set of 6 points is actually very good. If I give you something a bit nastier, like this convex pentagon and a point very close to this segment, then any partition you give me, say you give me this one, if I remove the top point of this triangle, it sort of breaks down. Okay?
Sorry, if you're giving us examples of that theorem, shouldn't you be taking 7?
Yeah.
Or are you telling us why?
This is an example of...
You're telling us why you need 7.
Yeah, and the cool thing is, we only know, so he proved that with this many points, you can always get a partition of this type. It's not known to be optimal in dimension 5 or greater. Even though in dimension 5, it's a question of whether for 12 points you can get a counterexample like that. So we even have candidates for the counterexample. It's just checking that they work, which becomes difficult.
So are all these terms use something like Gauss Coulomb, or are there other techniques that can be applied?
Let me see. For
The standard versicle and typical?
no, so for this one, so for versions like this one, there are no topological versions known, which are non-trivial. So the topological version of this one is completely open, even in low dimensions. The way Larman proved this one, he was proving actually a question. He was working on a question by Macmillan on if I give you many points in OR-D, you want to take with a projective transformation that set and place them in convex position. And they were much more geometric methods than before. Yeah, so the methods that work for this sort of problems are the usual linear algebraic methods that work for Tverberg's theorem, which I'll talk about in a while. But every problem that I tell you starting from this one, if you ask me, what about the topological version? Those are very good questions that I'm actually excited to work in. Okay, good. So, yeah. Now, this one, 2d plus 3 points is interesting. 2d plus 4 points is trivial, just to give you. So with 2d plus 4 points, if I give you 2d plus 4 points instead here, I could split them into 2 sets of d plus 2 and d plus 2. Get a random partition on this side. A1, B1, get a random partition on this side, A2, B2, and this would be my set A, this could be my set B. If you remove any one point, you're just breaking one of the two partitions, so it doesn't stop working, right? So 2D plus 4 points is trivial, 2D plus 3 you actually have to do some things. And this is, it's conjectured to be optimal, but we don't know, right? So it's natural to ask what happens if I want to extend this to Tverberg-type theorems instead of, so maybe I want to extend this to partitions into more sets, or maybe I want to be able to remove more points. And in both cases, you can do stuff like this. So slowly, people have gotten those versions. Let me go here. So the first of those was in 2007, Natalia Garcia-Colin. She was a student of David Lorman, and she was working on radon with more tolerance. The tolerance is the number of points I'm allowed to remove. Okay, so she proved that now with t plus 1 times d plus 1 points in OR-D, there's a partition AB such that for all C of at most t points, the convex hull of A minus C still intersect. Okay, so if I allow you to remove 7 points, maybe you remove 3 here and 4 here, or 5 here and 2 here. You're allowed to do this any way you want, but you'll never break a partition that you'll find here. Okay. She conjectured that this would work nicely in so this looks a lot like Tverberg's number. So she conjectured that with Tverberg's theorem, something similar happens. And in a joint work with Ricardo Strauss, we proved that her conjecture was true. So now I'll give you this many points. So you have the number of pieces you want, the number of points you're allowed to remove, and the dimension. And then with this many points in OR-D, there is a partition A1 up to AR, such that for every set C of at most t points, the intersection of the convex hull of AJ minus C so you get a non, I mean, if you try to do this argument here of taking 12 partitions over and over again, that tells you that you basically save 1 point for as you increase t. Okay, so every time t increases by 1, you save 1 point over the trivial bound. And we thought that since the number was so nice, it had to be optimal. But if you want a lower bound for this one, well, one easy lower bound is OR-T points, right? Because if I give you OR-T points and you split them into OR pieces, one of them has at most t points, and you can just remove that. It's empty. Its convex hull is empty. The intersection of whatever with that is going to be empty. Okay? So you have a lower bound of OR-T, and you have an upper bound, which is this one, where the leading term is OR-TD, right? Which is roughly OR-TD points. Okay? So the question then becomes, is the truth closer to what the pigeonhole principle tells you, or what these linear algebraic methods could give us back in 2012? And surprisingly,
it's halfway in between.
no, it's almost this. So this is a very recent result by Natalia Garcia-Colin, but now with a couple of co-authors, Miguel Raqui and Edgardo Roldán Pensado. Which proved that for fixed OR and D, so if you're only allowed to change the number of points you remove. The number of points needed, it suffices or t plus little o of t points. Okay? So the bound that the pigeonhole principle tells you is basically what's going to be true. The only disappointing thing here is that this little o is sort of pushing the limits of what you could consider by the little o. If you open this up in terms of or and d, since they used Ramsey-type theorems to prove something like this, it has exponential towers with size depending on d and t. Okay? So one thing I worked with is, well, what happens if, so since it's basically the combinatorics, the dimension is sort of fading away here, what if you try to do something even sillier and just make your partition randomly? Okay, so I'll give you, so the idea here is now given n points, make a partition into OR sets randomly. So you can think of having OR different colors, and every point you're going to point it randomly and independently with one of the OR colors, and you want to see if the convex hulls actually satisfy something like this. Okay? And it turns out that you can prove this theorem with those methods and get a much better estimate of what's going on here. You get something which is polynomial in all three variables, and here it actually it's bounded by like the square root of t instead of t. Okay? And you can even push it a bit further. So the most general version of this one, which is what I want to tell you about, is the following. So the theorem here okay. Before stating the term precisely, so this result is basically telling you that you can take t to be roughly 1 over OR, right? If you take a bit less than 1 over OR of the points, or a 1 over OR fraction of the points, right? So really n over OR points is what you're allowed to remove. You can, whatever your partition was doing, it's still going to be a total partition. And another way of looking at this is just as long as we keep more than 1 minus 1 over or well, a fraction of the points bigger than this, we should still be dealing with a total partition, right? We still have okay, so I have my big set of points here. So I want to give you a partition of them so that whenever I look at an epsilon fraction of them, the partition induces a total partition in those. Now, with the arguments I told you about with the pigeonhole principle, the number of points I should keep here cannot be smaller than this one, unless I give you more than one partition at the beginning. So I give you now m partitions. And in the small subsets, I look, and maybe the first partition doesn't induce a total partition here, but the second one does. So what I want is to give you n partitions and guarantee that in every small subset, I induce at least one total partition in all. Okay? So here I want to look at epsilon fraction subsets, where epsilon is bigger than 0. So if I give you the number m Well, I have the number m, the fraction epsilon, the number of ports or, and the dimension d. I want to know what the conditions they have to satisfy to be able to get something like this. For every such parameters and every set, I have n partition of them into R pieces so that when I look at small subsets, at least one of them induces a Tor partition. Okay? And the theorem here is that the condition I want is that epsilon has to be really greater than 1 minus 1 over R to the m. So the interesting thing here is the condition doesn't really involve the dimension, right? This seems that the combinatorics is overtaking what's going on here. The dimension sort of fades away when you have enough points.
How long does this result? I mean, January, February. We're only in March.
So it's, I mean, the archive version is December last year, and it's still going through the motions of, yeah. So it still isn't published, but you can see it in archive from last year, yeah. Okay. So the big statement here is that if you have this condition, then for any sufficiently large x, there are m partitions of x into R ports each, such that in every epsilon fraction subset, at least one partition induces a Tor partition. Okay? And there are also bounds for what do I mean by sufficiently large, but it's polynomial in all the variables that really matter here. Okay? When m is equal to 1, that's precisely, this contains the Garcia-Collin-Raggi Roldan-Pensado result. Okay? So I want to convince you that this is true. And then, if I have enough time, I will try to convince you why this should not be true, or at least it's counterintuitive that it should happen. Okay? Questions so far?
I would guess a referee then, if it's counterintuitive, it's going to say this can't be true. It just doesn't seem true. Are you ready for that comment? Or did you address it in the introduction?
Yeah.
It seems unbelievable. Really, 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 my proof is right. Those are the best results.
Right, so I'll tell you some things about the proof here, and many things have to be right on the edge. I mean, the proof seems like it's very relaxed, but if anything in the proof could be improved, then this would be improved substantially. So it seems odd that so many things in the proof which seem to, like you're giving yourself a lot of space, you're not really giving yourself that much space. Okay. So let me tell you about the techniques you can use to prove Tverberg-type theorems and how it applies to this thing. So for proof methods, before we get, so the last flow for this will be the probabilistic method, but let me tell you the classic proof method for Tverberg-type results. Okay? And the idea is to take your points in ORD, lift them to a higher dimension where you can reduce Tverberg's theorem to something simpler and work with those. Okay? So it's basically an idea of lifting your points to a higher dimension. And if you look at Radon's lemma, where you have d plus 2 points in ORD, I told you that this was basically just a basic linear algebraic fact. You take your d plus 2 points, you have an affine dependence, which means that you have a non-trivial affine combination of them that gives you the 0 vector. where not all the coefficients are 0 and the coefficients sum to 0. So some coefficients are positive, some coefficients are negative. The points with positive coefficients make one part in the partition. The points with negative coefficient make the other part in the condition. And for a long time, there was a wishful thinking of doing this for Tverberg-type partitions. If I could only get coefficients of 3 types and get Tverberg partition into 3 parts with a similar argument, I would be done with something like this. Okay? And the trick here is to actually formalize something like this. So first off, I have to come up with the coefficients I want to use. And so the first trick here.
So some kind of polarization?
A tensor product. Yeah. So the idea is to take V1, V2 up to Vr vertices in a real space of dimension r minus 1 of a regular simplex centered at the origin. Okay? So the way I'm going to lift my point, these are going to be my coefficients in some sense. And now, given a point in RD, the first thing I do is I add a coordinate 1 to it. So I place my points as a hyperplane in RD plus 1. This is just to transform an affine problem to a linear problem. And then what I do is I consider the points of the form Pj tensor A1, right? So I take the tensor product of this magic points I got here, and then this point I constructed. This lives in dimension r minus 1 times d plus 1. So you start seeing Tverberg's numbers sort of appear by themselves, right? And the big result I'll use here is, well, let's notice one thing. If I do this with every possible j, v1 tensor a comma 1, v2 tensor a comma 1, up to vr a comma 1. When I add these points together, since they are tensoring the same vector here, it's just basically adding things on the left side. And this side, they add to 0. Okay? So here, since the sum of them, since the barycenter of these points is the 0 vector, the convex hull of these points contains the origin. Okay? So what I want is a strong, I want something to tell me about when do sets capture the origin in their convex hull. Okay? There's a very nice result of this type called the colorful Carathéodory theorem, which says the following. So suppose I have here the origin in Rn, and I give you different color subsets Let's use the fancy chalk. So suppose, for example, in the plane, I give you 3 orange points, 3 yellow points, and 3 red points, so that each of them captures the origin. Okay? Each color in their convex hull has the origin. Then you can find a rainbow set, taking 1 point of each color. I hope I can do this right. Yeah. So that the rainbow triangle captures the origin. Okay? So this is a very nice theorem by Imre Barany, from 1982. And what he proved is that given n-1 sets that capture the origin in Rn, there is a rainbow set that captures the origin. Okay? I'm purposely changing the dimension to n here, because what I'll be doing is, whenever I give you a point in RD, the column of points I mentioned there captures the origin. So as long as I give you the dimension of that space plus 1 columns, I can pick 1 from each column and they capture the origin. And that induces a two-order partition. Okay? So if we take n equals or minus 1 times d plus 1, then the big reason this transformation works is, and I'll call this the magic lemma, is that two-order partitions in RD correspond one-to-one to colorful Carathéodory selections, or to, yeah. In this high-dimensional space. Okay? So if I want to say something about these things, I just translate it to the high-dimensional space and say the same thing for the colorful Carathéodory theorem. This one is easier because figuring out if something contains the origin in its convex hull is, at least for me, easier to track than whether all convex sets actually intersect or not. Okay? Okay. So the first thing I need to do is to translate that theorem to something about colorful sets capturing the origin. And so the equivalent version of that theorem is now the following. We're going to be given, so here, if I was given big N sets, big N points, which is the size of X, given N color classes in Rn, each of R points, each capturing the origin, zero. What I want to do is, what I want to do there is to find M partitions. So here what I want to find is M rainbow sets. We want to find, well, we can find M rainbow sets such that for any epsilon n colors, right? This is, instead of looking at a small fraction of the points, I look at a small fraction of the colors. And among these colors, at least one of the rainbow sets captures the origin when I restrict to those colors. Okay? Such that among, yeah, for any epsilon n colors, at least one of the rainbow sets captures the origin. Okay? Oh, I'm assuming that epsilon is bigger than 1 minus 1 over r to the m, and n is very large. Okay? So with the same conditions I had there, I just translate it directly to this one to see exactly what it means in this dimension. The cool thing is that if I want to check if a set captures the origin, I just have to show that there is no hyperplane separating it from the origin. And this is nice because Let me give you one lemma. Okay. Before doing this, so actually, let me give you x in or n, and suppose I give you a subset of x. Okay, I want to know if this subset captures the origin. Okay, so y capture 0. This is the same thing as saying that 0 is in the convex hull of y. If and only if, for every half space H containing the origin, we have at least one point of the set. Okay? Initially checking this sounds difficult because the number of half spaces I have to check is infinite, right? I just have to check every single possible half space that contains this one. But if I know this x in advance, and this is not very big, for any subset, I don't need to check an infinite number of hyperplanes. But we only need to check something which is the coordinality of this set to the n many hyperplanes or half spaces. And this is just by checking how many combinatorially different half spaces you can have with respect to this set here. Okay? So this is the reason why this is interesting is because this is polynomial in terms of the number of points of x here. If your dimension is fixed, this is not too big. Okay? So now I'm actually ready to use the probabilistic method. So my rainbow sets or 1 or 2 up to or m, I'm going to construct them inductively. So first I'll make or 1 so that things are very nice, then or 2 so that things are very nice, and so on until I get to the last one. And so let's start with how I make or 1. Okay? So what I'm going to do is for each color class F, one of my colored sets, I'm going to choose a point here randomly. So this has all points by the conditions on the problem, and I'm going to choose it randomly and independently for each color class. Okay? And what I want is to have a set that contains captures the origin with a large tolerance. Even if I remove many points, it still captures the origin. Okay? So if I look at any half space H that contains the origin, well, let big XF be the random function so that this is 1 if my chosen point is in H and 0 otherwise. Okay? Actually, I'll call this, yeah, like this. Okay? So I do this for each color class, and this initially forms OR1. Okay? So OR1 intersection H plus, the number of points I have from OR1 in here is just the sum of these variables for all color classes, right? Because they are contributing 1 if the point is inside and 0 if it's not inside. So this is the sum of these variables over every color class, right? And this is a sum of independent indicators where I have some information about the expectation of these things. What do I know about the expectation of these things? The expectation of this function is at least 1 over O, right? Because since my color class captured the origin, at least one of the points had to be on this half space. And so I have a sum of independent variables. I know something about their distribution. They just give me 0 or 1, so they can't. The range cannot be infinite. It's just be of length 1. And I have information about their expectation. This tells me a lot about how this is distributed. I can get very good bounds called large deviation inequalities, which tell me how this is actually clustering. Okay? So one of those nice inequalities Hoeffding's inequality tells you that in this situation, the probability that this sum is less than its expectation minus lambda. So the probability you have its expectation here, the probability that you're far away from the expectation on the left side is bounded by e to the minus 2 lambda squared over n. Okay? So if I fix this lambda here, you get something of this type. Okay? Now, the interesting thing here is that this is not one of the nice checks. Here I have an exponential decay. Okay? And this is really what's doing all the work here. Because then the probability that the number of points I have here, or one intersection H plus, is less than n over or minus lambda. This is the expectation or bigger than the expectation, right? So this should be more difficult than this. So this is less than e to the minus 2 lambda squared over n. And I will say a half space is bad if this happens. Okay? And I only need to check that many half spaces. In this case, X is n or, because this is the total number of color classes I have, and each of them has or points, right? So the probability that there is one bad hyperplane, or half space, is less than, well, I don't know if they are dependent or not, these probabilities, but the union bound still holds. This is less than the number of possible cases I have, n or to the n, times this, e to the minus 2 lambda squared over n. So as long as this is less than 1, I will have one configuration of points where this never happens. Okay? And for this, you just need, you can set this equation and solve for lambda, but it basically gives you lambda being roughly the square root of n. As long as this cancels and you go a bit overboard, since here you have an exponential decay, the polynomial growth you have here is overwhelmingly smaller than, even though this can be very large, this becomes much smaller than that, okay? And this basically tells you that, so what does, this tells me that if I remove less than this many points, every half space still has at least one point on the good side, and so the set still captures the origin. Am I well on time?
Yeah, I think you started like 12 minutes late, so you've got like 15 minutes.
Okay, perfect. Yeah, more than enough. So, so what's going on here is, as long as I remove less than this many points, I still capture the origin. I haven't removed enough to break one half space from having points of my set, right? So this means that OR1 resists the removal of roughly n over OR minus lambda points. Okay? I'm leaving it this way. Lambda is much smaller than n. As long as I had here little o of n, it would be okay. I have square root of n, which is very well on the side of things I want. So what this is telling me is if we keep at least n minus this, n minus n over OR minus lambda, at least this many colors, OR1 captures the origin. Okay? At this point, and this is sort of what we were aiming for when m was equal to 1, right? At this point, this implies the Garcia-Collin, Draghi, Roldan-Pensado theorem. The observation to make sure that you can continue to do this, so this is our choice for OR. We make a choice of OR1 that satisfies this, and then we want to move on to choose OR2. To choose OR2, and I'll be a bit vague about this one. So now we move on to choose OR2. So I want to choose OR2 so that if I take a large enough set of colors, either its restriction to OR1 captures the origin, or its restriction to OR2 captures the origin. Okay? So if a set of colors if the restriction of a set of colors to OR1 does not capture 0, I want to understand how this can happen, right? It means that one hyperplane separates it from the origin, and it has to be one of the hyperplanes that we found here, okay? So at least one of the n OR to the n special hyperplanes separates it from 0. Okay? So let's call this hyperplanes H1 up to H and OR to the n. Okay? So I can look at, so think of OR1, and I can look at which colors are separated from the origin by H1. Okay? So let M1 be the set of colors which are separated by H1. M2, the one separated by H2, up to M whatever, those which are separated by the last one, okay? So my rainbow choice OR2, so if I said when I restrict it to OR1 doesn't capture the origin, it must be a subset of one of the sets of colors, because it must be separated by one of these hyperplanes. So when I do my recoloring, I just need to make sure that whatever was happening on that side, whatever argument was working with the probabilistic method, it works simultaneously for these sets, okay? And the number of bad cases just increases by a factor of n OR to the n, okay? So now we sort of repeat the argument. Yeah. We do this again. for M1, M2, M2, and or to the n. So what we want to do is to choose each color class randomly now in R2. For each hyperplane, we want to, we make this random variables, but now depending on which of the bad cases we're talking about, and we want to see that this is not too far away from its expectation, which we have under control because of the same inequality we had before. Okay, so it's essentially the same argument now inside each of those cases, and you have some exponential decays which are going to come from the large deviation inequalities that we'll be using. The number of bad cases you have, instead of being n or to the n, is going to be n or to the 2n. So for each of those sets, you're going to have n or to the n bad cases, but it's still going to be polynomial in the number n that you're using here. Okay, so if you do things carefully, the exponential decay is going to 0 so fast that even in the worst case scenario, you're overtaking every bad possible thing that could happen. Okay, and then when you move on to the third set, the number of bad cases just keeps increasing polynomially. Your exponential decay keeps being exponential, and so you can keep doing this. And if you keep control of how things are decreasing in size of the possible bad sets, you always lose a factor of 1 minus 1 over r plus something that becomes very small compared to this. So as long as you want this to be, as long as you take epsilon n sets, you just want, if you, as long as this number is bigger than this one, the extra errors you get here are not going to be very large enough to overtake and flip the inequality. Okay? And the surprising thing, so if here you have this to the nth power, you just want this epsilon to be bigger than that. Any questions so far? Well, this basically gives you a bit of an informal idea of the proof. The reason why I think this might be counterintuitive
How long is the proof in your paper? I mean, because you're saying, well, you do this and we want you to ignore these, but presumably you're more detailed in the paper. I just wondered
yes.
how long that makes the argument.
The paper is about, I think, 10 pages,
Oh, that's not bad.
but that's because most of the paper is related to an extension of that to what we call Tverberg-type theorem. This argument itself, if you write it down nicely, it's about 2 or 3 pages, but it's a very careful induction in which, it's a bit too many details to give out like that. Yeah, I prefer to give the main idea here. But so what's going on here? If I give you a set of OR points capturing the origin, and I take a random hyperplane around the origin, I should expect OR over 2 of the points on that side, right? So whenever I'm saying that the expectation of my variables is at least 1 over OR, this is only if the half space is very unlucky, right? It only had 1 point on that side, but I'm doing this over all hyperplanes. So it seems strange that I cannot say, if I could improve on this thing here, it would jump right back in here. So it seems a bit strange that, and I know I cannot improve this just by the pigeonhole principle. It's not something I will, I mean, the condition on epsilon is necessary and it's sufficient, but in the proof it seems that this is being a bit too relaxed. And so the very bad hyperplanes or counting too much compared to the other ones when we take the large deviation inequalities. So every single one of these hyperproblems has its own normal distribution, ideally, and the very bad ones are strong enough to pull everything back to their side, right? Even though it seems that 1/2 might be something you get here, you could potentially get here, 1/r is really the thing that's pulling the weight here. So let me mention one thing about the topological versions, because you mentioned some things about Borsuk-Ulam. If you're unfamiliar about those things, and just to give you a very large family of open problems, so if I give you n points in RD, I can think of a simplex of dimension n minus 1 has n vertices, right? So this big simplex has n vertices. So I could make each vertex here correspond to each point here, and it induces a map from the vertices to RD, and I can extend this map linearly. Okay, so we can extend linearly. And the cool thing is that if I look at any face here, the image of this face is precisely the convex hull of the corresponding vertices, the image of the vertices of that face. Okay? So Tverberg's theorem is really a theorem about maps, linear maps from high-dimensional simplices to low-dimensional real spaces. Okay? It's telling you that for all linear maps from here to RD, there are disjoint faces of the simplex whose images intersect. Okay? And so whenever you want to work with the topological versions of this, it's asking, well, do you really need linear functions? Or could you get something like this with continuous functions? If I take a high-dimensional simplex and I squash it any way I can to RD, do I get this or disjoint faces intersecting, or it's something I don't get? And we have a rough idea. Well, now we know that there are Tverberg-type theorems which need the linearity condition. There are some conditions on the parameter R which are a bit surprising that appear. When R is a prime power, you get the topological version of the optimal version I told you from the 60s. If R is not a prime power, very recently we know that you cannot get the topological versions with the exact number. If you get a bit more points, you might get something like this. But every version with tolerance, if you ask for the natural version with continuous maps instead of linear maps, it's, as far as I know, an open question and a good one to think about. Even Larmont versions with 2D plus 3 points, the topological versions. And I think that's as far as I wanted to go in the talk.
All right, well, thank you very much. Are there questions, comments, topology comments? Yes.
So can you ask any of these questions and answer any of these questions for configurations of points in other manifolds than Euclidean space?
In other manifolds, off the top of my head, I don't think so. I think there are some versions on the sphere, but there are like sporadic results, not something generalized.
Need a metric, right?
Yeah.
Geodesic convex hull.
I mean, there are some things for convexity spaces. Rather than going to manifolds, you axiomatize convex hulls. And there are some results like those. But it seems that it's... So there were some big conjectures in the 60s and 70s about what should happen in the in general convexity spaces, and they don't really seem to work. Later counterexamples were found, and there's a very nice conjecture by Eckhoff who said that if you have Radon's theorem in a convexity space, you should have Tverberg's theorem with the optimal number of points, and that was sort of the big conjecture in the field. And there's an archive paper by Boris Book from 2010 which disproves it. It hasn't been published as far as I know, so you could still not believe in it if you don't want to, but I tried to read, I read it, and it seems correct to me, the counterexample.
Are there other questions? Comments? No?
Counterexamples?
Counter? All right, well then let's thank Pablo again.